Actually, I changed the third practice task. Before, I thought that I will give you the closed kinematics, but for me it's not interesting anymore. I mean, for me personally. For you, it will be a nightmare, actually. And still, if you want to do this, you can do this for your own. But what I would like to do is to give you a practice which will be connected with the lecture material. So, in order to make your life even easier, I decided to base the third task on your second task. It's like we're gonna use something that we already know. The model from the second practice task as the basis.
Which one?
Your own variant that you already done. You already been given with your variant, so you need to use the same variant. Any of them, because it's not really important right now. So actually, we just need something that moves. For example, right here, I'm using a model with the PID control, but the same will be true for any other kind of control. We do not worry about how it is controlled right now. So the only thing that I have changed here is marked with this box. So what have I done? First of all, I just solved the direct kinematics. I have calculated the twist, and I have calculated the V, the something like the P dot. How have I done it? So here there is another piece of script which is called spatial kinematics. If I open it up, you will see the following. So actually I need to clear everything. So here you can see a bunch of references. So this is the video, which is very great in the book, and a piece of text. So actually I need to copy this thing right here. So by this function, I added additional functions. So those functions I have downloaded from wiki page of the book of Kevin Lynch. Then I'm using here symbolic multiplication. And just like here I have denoted all the variables that I would like to leave as a variable. Here it will be Q1, Q2 is the position of first and the second link. It is the velocities, angular velocities, the derivative of Q1 and Q2. It is the forces, but right now actually we do not need it. So this is the something that is going to change. And in the second line, I have put it a constant values, but actually we can put it in just one sim. So here it is the vector of position, vector of angular velocity, and then I'm starting to assembling everything for the example that I just showed you. So angular velocity for first link. So The first link, can you tell me around what axis it rotates? Y. And minus y. Because it like y orientated not like this, but like this. This is y minus. And the second one also minus y. This is why I have a 1 for the y and with the minus. For the first and for the second one, so the joint for the first link coincide with the initial world frame. This is why zeros for the R1. So what will be the R2? L1, 0, 0, because I have an offset for the x component. L1, 0, 0. Then I'm using this function vect to SO3. It's like the SO3, it's Lie algebra. The conversion from a vector form to the skew-symmetric form. And I'm doing the calculation with R, and it allows me to compute these twists with the direction, with the one with the hat. In the Lynch, those are called as a screw axes. So the bunch of for the angle velocity and for the linear velocity. Then those are the homogeneous transformation matrices for the initial state, for the old centers of masses. For end effector, now you can see the Rodriguez formula. This is the formula typed in code, and you can see the result, that it's really the rotation around y-axis. Do you remember that we just derived manually? And here you can see that actually we don't need it to derive manually. We can just write a code, and it's very convenient. Then we have this matrix for the H. Abster, it means absolute terrible. It is this ugly expression for the P, the long one. So here you can see the rotation matrices and this absolute terrible expression. So everything is put in there. Then I'm using the bracket formula to solve the direct kinematics, right? And so this is the H, the homogeneous transformation matrix for the end effector. And from here, I just took the vector for P. Okay, can you see it? So then the Jacobian. So here you can see the Jacobian one is just the S1, the screw axis. As for the Jacobian of the second link, we need to use the adjoint. So just like in the equation that I just showed you. So if we put everything inside, we will have the Jacobian. And this is the everything that we need to do the task. So if I do this, you see all the components are calculated. And by P, I have the direct kinematics. So this is the function, actually. And J2, it is the Jacobian. So now we need to go here. And direct kinematics is nothing else as this P that I just derived. Twist, it's just Jacobian times vector of angular velocities. And V is this thing. It's twist time position of a point that we would like to have, like you see. So here twist in a vector form, right? Six entities in the joint in the column. And this is why T is in vector form, and I am using this vector SR3 to transform from vector to the matrix form, and then it's multiplied with the P. P is calculated due to the direct kinematics. And now, actually, we can create plots. Okay, yeah. In my example, I haven't done any plots, but it is your task to consider what kind of plots should you do.